Okay, we can start. Welcome, everybody. Thank you for joining us today for Operate's fourth webinar on the use of drone for weed management. My name is Fanny Presman. I'm a project manager at the French Vine and Wine Institute, and I will be chairing this webinar today. This webinar is organized as part of the European project Operate, which aims to exchange and share knowledge on alternative weed control in Europe. And we will begin with a brief presentation of the project, followed by technical presentation on the results of experiments using drone in Europe, in Greece, Spain, and Sweden. And to finish, we will have a concrete example presenting the technology developed by the company Spraydrone. So during this webinar, you are all muted, but you can ask questions using the button, the question button at the top of your screen, and we will take 5 minutes after each presentation for questions. So I give now the floor to Olga, which is the Operate Coordinator, and she will give us a very brief presentation of the projects. Olga, it's your turn.
Thank you, Fanny. I hope you can see my screen now.
Yeah. Okay.
Perfect. Thanks so much. Hello everyone. Welcome to our fourth webinar on drone technology applied to weed management. My name is Olga Kriezi and I work as a research associate at Agricultural University of Athens and the Smart Farming Technology Group. Our project coordinator is Professor Spiros Foutas and I am the project manager of Operate. So just a brief introduction to our project. Operate is a European thematic network having as a base 8 operational groups and focusing and supporting alternative weed control solutions. So our main objective is to build a self-sustainable multi-actor EU-wide thematic network to support, promote, and let all the relevant stakeholders know about non-chemical weed control, alternative weed control. As I told you, our base is the 8 operational groups from 7 countries. So we have France and Italy that are focusing on cover crops, the France on the under rows, and in Italy we have self-residing cover crops. We have Spain with new biocides based on natural oils. In Latvia we have a robotic laser that locates the weeds and destroys them. In the UK and Greece we have camera-guided mechanical weeding. Also in the UK, we have a second solution with an electrical weeder. And in Sweden, a similar solution that we will talk about in today's webinar. They use drones to create maps and locate better the weed to have specific herbicide application. So about our methodology, we are building 7 national networks, one of each country, and this is why, because we want to have a specific and to learn about specific needs of each country and to have our solution based on their needs. We have created a survey to capture needs and barriers that hinder practitioners to adopt alternative weed control solutions. And also we did a literature review on all the available solutions out there. So we gathered every solution, both scientifically and commercial, and we stored them to an inventory. So having this, we selected for each country specific solutions that underwent through 2 rounds of evaluation. And now we are picking them as best practices and we are disseminating them properly. In parallel, we are organizing demonstration events, an e-learning module, and of course, cross-fertilization activities such as cross-visits and this day's webinar. And we are introducing to people, stakeholders, students, researchers, farmers, alternative weed control solutions that may be interesting to them and they want to adopt. And here is a brief glimpse of our inventory with all the alternative weed control solutions out there. And also our results are videos, our inventory, demo events, podcasts, practice abstracts, fact sheets, and more to come. So thank you so much.
Great. Fanny, will you make an introduction or shall I just continue straight ahead?
I think just go ahead.
Okay, perfect.
Yeah.
So let me share my screen first. I will welcome you as well. I'm the second presenter. I am Vasilis Psiroukis, also from the Agricultural University of Athens. I work in the same group as Olga, the Smart Farming Technology Group. And today I will be leading the session for spraying drones and their applications towards alternative wind control. And we will also showcase a bit of the experimentation, let's say, aspects of UAV drones. We will first see a few things about regulatory aspects because it's quite a delicate subject at the moment. And then we will, of course, see some results and some trials that we have conducted within some other projects that cooperate with our current project operate, of course. So, to start with the presentation, I have a brief layout that I have already explained, and to not waste any more time, I just want to give a very brief introduction of what spraying drone is for those that might not be that familiar. So spray drones pretty much is any flying machine that is capable of applying for any agrochemical at a desired rate close to the canopy. And that close to the canopy usually refers to an altitude of 5 meters above ground level, maybe less, maybe 1 meter or two higher. But in any case, we talk about a platform that operates at very close proximity to the target. And this is a very critical aspect because, as we will see later on in the legislations, the main reason that UAVs are not as widely adopted as they might, some might consider that they should be, is because they are not commercially, let's say, legally to be operated at every case. So, this technology, however, has been very popular for some years now with farmers, and this is something that we have seen in numerous EU countries. For example, in Greece, if someone travels to the northern parts where a lot of maize fields or cotton fields or rice fields exist, you will encounter a very futuristic, let's say, landscape where you will see left and right various fields that drones fly over them. And that's for a reason. That's because UAVs, spraying UAVs, have numerous advantages compared to terrestrial machineries, and of course, farmers have identified them and they have adopted them. Now, what are these advantages? So first of all, this is not something directly related to herbicide applications, more or less crop protection applications. So when we apply fungicides, for example, which is very commonly used, or also growth regulators. So whenever we have a certain crop with thick foliage, uh, from an engineering perspective, drones tend to be very efficient because they can easily penetrate these layers of foliage and they can actually provide a more homogeneous, let's say, spraying profile. Now, on a more direct benefit to herbicide is that they practically eliminate soil compaction. There is no machine stepping on the field, so they eliminate that entirely. And a similar advantage is that because we have no terrestrial machine cruising the field, they actually eliminate dangers related to potential accidents with terrestrial vehicles. When, for example, we have a field with a very steep slope, there is a very high risk that the terrestrial machinery, especially when carrying a heavy sprayer with it, it might flip over. And that, of course, does not apply to drones, where they usually have altitude regulation sensors, something like a simple 2D lidars, for example, active sensors, that they can simply follow the terrain and make these applications without any risk for the operator himself. And similarly, again, I will talk a bit about the northern countries, the southern countries, excuse me, where we traditionally tend to have some outdated, let's say, fleet of machinery. It's very common to see farmers conduct spraying applications with literally no protection whatsoever. And here, drones can also offer an advantage because they operate remotely. They are not close to the operator. So when we have, for example, a very dangerous agrochemical for human health, this distance actually safeguards the operator. And then finally, because we talk about a machine that is usually comes integrated with highly accurate positioning systems such as RTK GPSs, they do enable highly targeted applications of low dosage compounds, and that's because practically they can carry a very small let's say, volume of agrochemicals, and we tend to do what we call ultra low volume applications. We end up with a very thick spraying solution, and this all comes together with the highly targeted abilities that they offer. Now, as explained already, the basic methodology is that we design a flight path beforehand, and similarly to monitoring drones that some of you might have already operated, we determine the parameters of the flight, such as the altitude, the speed, and now instead of photo capture, we have a spraying application. Everything is designed beforehand, and then we just send the flight plan over to the drone, and it executes it operately. It comes back whenever the tank is empty, whenever it needs a battery change, etc., etc. So, before we move to the legislative parts, application theory, why is it so, why people think it's good? And there are several engineering principles behind it. And one of the most, let's say, fundamental ones is that because you have a machine that roughly weighs 40 or 50 kilograms, and this machine tries to levitate, it requires a substantial amount of energy to do so. And this energy comes from the propellers that creates a downwards, what we call the downward currents. And these currents have double benefits. They first of all, as we explained already, they make the droplets penetrate the medium levels of foliage of canopy easily. And also they create a barrier that prevents the droplets from escaping from the target area. And this is a very critical parameter identified by the EU as well, as we will see in a bit. Okay, we have this solution that has several benefits. It's not, of course, an opium. It cannot we cannot blindly say that it can be applied everywhere, but it has some benefits. But for some reason, this solution cannot be widely used because it is considered an aerial spraying, and from significantly old, let's say, EU agricultural legislatives, aerial sprayings are prohibited, except, of course, for specific permits that enable to do them. So, for example, if you have a very steep slope and a topographical, let's say, survey, in most countries, a permit might be applied. But nevertheless, they are prohibited. Although, as you can see in the final bullet that I have here, the EU has been actively trying to change that. And for that reason, they have recently, and by recently I mean 2 years ago, they have started promoting EU's spraying UAV-specific research topics under Horizon projects, which is arguably one of the largest, let's say, EU funding schemes, where they actually provide funding for research to be done so that concrete evidence can be collected and so that whole legislation part can be eventually updated, which will include several benefits like the manufacturers of agrochemicals. They will be able to create UAV specific products because right now we just borrow the conventional ones and we adjust the dilution rates, which is okay, it works, but it is not optimal, of course. And the other challenge that we face with spraying drones is that similarly to any other piece of spraying equipment or spraying machinery, there are a lot of false notions associated with its usage. So, for example, for spraying applications, a lot of farmers are convinced that the more I apply, the better results I will get. And this, as you might know, it's associated with numerous benefits from ending up creating toxicities within our own fields to higher tolerance, all the way to just having very high drift rates. And this drift rate, especially, is something I'm going to focus heavily in my presentation because it's a very critical part and one of the major threats coming from the agrochemical contamination coming from agriculture, as it has been identified by the EU. So drift is essentially the displacement of any form of droplets or agrochemicals in general from the field of application to neighboring areas. So these neighboring areas might be high-risk areas like water bodies or populated areas, or in most common cases, we end up applying the same agrochemicals to a neighbor's field, which then stacks and creates undesired phenomena. There are two types of drift: particle drift, which is the direct one, and the other one, vapor drift, is when we have residues of agrochemicals. They end up evaporating due to being in open field conditions, and these airborne now substances do travel quite some few distances. And drift is one of the three major pathways of agrochemical contamination. The other two is leaching and runoff. But because the drift is the first one that can be mitigated, this is why a lot of research is focused on that specific part, because with proper application and proper knowledge, it can be mitigated. So, why drift is very important? I will not say a lot of that because it makes total sense, and I think most of you have already understood that by losing agrochemicals, I end up with lower deposition rates where I want them to be. So in my field, I actually end up sending them elsewhere. I increase the cost of my applications and I get nothing in return. So of course it increases production cost with no benefit whatsoever. And when I talked about mitigation, similarly to conventional spraying equipment, the first thing that comes to mind is the application end, so the nozzles. Heavier droplets are usually more resilient to wind, so they are more difficult to be swept away by the wind. And this is why anti-drift nozzles usually produce larger droplets. On the other end, lighter droplets, they do have the advantage that they can sometimes penetrate foliage easily, but again, they can be much more easily to be swept away. Now, for drones, the specificity that we have compared to terrestrial machinery, we have an additional, actually two additional parameters. Operating parameters such as pump pressure, cruising speed, but in UAV, because they levitate, we have two more. The first one is the altitude of the aircraft, and the second one, because we have that altitude in row crops, we can actually be more flexible with the positioning of the aircraft. So as you can see here, for an example, in a research that we have conducted in vineyards, one of the parameters that we tested was the positioning of the drone related to the rows, whether the drone being directly above a row or between a row. And again, creates a very complex system because this has to do with the wingspan of the drones and, of course, the spraying angle of the nozzles. So now that we have seen pretty much what happens with the spraying itself, I'm going to say a few things about the experiments we have conducted so far and we continue to conduct. So we try to first of all test and assess how well this new machine works and whether it is apparently able to replace conventional sprayings eventually when they become widely available and the legislative barriers are lifted. And of course, because it's pretty much a new technology and there's new uncharted grounds here, we try to identify as many risks as possible and create relevant strategies to eliminate them. So having said all that, I'm going to move a bit to the experimental design and show how experimentation is done in this field. So practically there are two things that we care about. The first one is how well we spray, and how well I mean spraying quality, how much coverage, which is usually the most important aspect, is achieved. And then the other one is how efficiently we spray and how much agrochemicals we lost. And there are two different methodologies for that. For the spraying quality one, we usually spray with deionized water because there is no reason to apply agrochemicals here. We just want to see how specific configurations tend to be translated in different canopy coverage rates. For the other one, for the efficiency, however, it's very common to use a color tracer, again, a harmless substance. It's actually edible, but we usually use tartrazine, and we end up retrieving this concentration of this tracer through laboratory methods. So, a few images. Here's a very quick experimental design for canopy coverage. As you can see, we have two different configurations, as I mentioned already. The one, the drone is positioned directly above a row, which is the over-row application, and the other one is between them, so inter-row application. And every yellow box that you see here actually translates to this type of collectors, which are water-sensitive papers, which actually change color upon contact with the liquid, and we then can simply use something like a binary mask, a very simple image analysis technique, and acquire the coverage rate. And for that, USD's the deposit scan software is the golden standard. This is what most researchers use, and we end up getting the coverage across different positions of the canopy. So for example, if we have a 3D crop like a vine, we position WSPs, water-sensitive papers, in different canopy heights, And we also have the additional parameter to study, which is ground deposition. And in drones specifically, that's very important because the nozzles are directly oriented towards the ground. So in some configurations and in some spraying strategies, we might have some good results with the canopy coverage, but we also increase the ground deposition a lot. This is a desired phenomenon, let's say, for herbicide application, but it's not so much for fungicide or insecticide applications. So again, we have to be very careful with everything. Now, very briefly, an example and a layout of a single experimental trial. So you can see how different parameters are combined. We have different height parameters, different speed parameters, and of course, the positioning of the draw, that being over row or inter row. And another critical and arguably the most important one when we talk about any form of experimental trial in spraying is the wind, is the environmental conditions. And for that reason, we have standardized procedures. In our case, we have an ISO protocol that we have adopted from conventional machinery. And we have very strict barriers within which a repetition, an iteration is considered valid. If, for example, we start spraying and mid-application the wind changes or we have very high wind speed, this application is cancelled. We gather everything, we gather every collector, we discard them, we set again everything, and then we repeat it. So it's actually this whole, let's say, field of field trials in spraying is quite a tiresome and time-consuming, let's say, series of experiments. But again, that's why someone has to do it. So, moving from canopy, I will now talk a bit briefly because I don't think I have a lot of time left. I'm going to show a bit how drift is measured. Again, we have an international standard, an ISO protocol adopted, which comes from terrestrial machineries. So it's ISO 22866, which is methods for field measurements by drift. And this ISO provides a very detailed plan on how drift should be measured. For example, where ground collectors should be placed, where airborne collectors should be placed, where the weather station should be to avoid having deviations due to the currents of the turbine or the drone, in our case. And here are some photos, for example, from our applications. Every white spot that you see in the first photograph is actually filter papers. There are collectors that allow us to collect the tartrazine in the different locations from the last application row. And then we collect the samples, we take them to the laboratory, and through phasmatophotometry procedures, we end up getting the concentration in different distances. And following the equations from the ISO, we end up with these drift curves. So the drift curves actually show us how different configurations, that being nozzles or operating parameters, end up affecting drift, starting from 0, which is technically the 1 meter away from our application area, all the way to 30 meters, or some might even want to go further. But the ISO states that up until 30 is the most critical area. So this is what most researchers end up studying. And finally, ground deposition, as I mentioned already, can be done either with traditional means, namely filter papers or water-sensitive papers. But in some more delicate cases, sensors such as the Vasilis P15 that I have on the right side of the screen, they can be used that actually, they do not directly show deposition, but they actually give characteristics about droplet diameter, and that can also be associated with what droplets end up hitting the ground more often and what else remains on the foliage. So very briefly, some results. Here I have a few results from the initial run that we had in vineyards back in 2022. Yes. And as you can see here, for example, switching from over-row to inter-row drastically affects the distribution of the agrochemical, because inter-row applications are much more susceptible to wind. And this is extremely important in my opinion, because usually most spraying advice software tend to give some green lit areas. For example, if the wind is between 1 and 3 meters per second, then go ahead, spray. But as you can see here, even within these green lit limits, if we go with a false, not false, but a specific, let's say, operational configuration set, then this is going to produce a completely different profile between two rows that are sprayed at the same time. And then some, again, engineering practices in principles in practice. As you can see here, when we increase pump pressure, this creates smaller droplets because we force liquid to pass through an orifice of the same diameter with much greater force. So the droplets break down the smaller ones. And this creates a phenomenon where the smaller droplets can penetrate the medium layers of foliage easily. But as we mentioned already, this is a balance. It's a trade-off relationship. So these are more easily swept away by the wind. So again, we have to consider everything and what we want to achieve. I'm not going to spend a lot of time here. I have some results from a recent publication that we have in collaboration with the University of Sassari in Sardinia. And as you can see here, we have various treatments. And from, let's say, a very general result from everything that we have studied here, when the drone flies slowly, it has better coverage. Okay, that's nothing out of the box here. However, being a bit more remote from the target actually produces better results, which was quite a nice find because one would expect a different to apply. So for example, here, as you can see, the general, let's say, guideline that we have produced from 1 year of experiments is that a flight altitude of 2.5 meters and a flight speed of 1 meter per second is ideal when we want to target the foliage. So, and then finally, that's the final slide. I have compiled pretty much everything that we have done, every research that we have done on drift in vineyards for the last 3 years. I have created this average curve. And for me, what's very interesting is that drones are exceptionally good at mitigating spray drift. So as you can see, the green curve is the terrestrial operations, and then the orange one is overall, blue one is interrow for drones. And as you can see, it's past a certain distance, 7.5 meters to be precise. Drones have actually so little drift that are not detectable with the laboratory methods used by the ISO. So for me, that's actually a great result because it's what the EU wants. So it's not like concrete evidence thereafter that drones have absolutely no reason to be considered in aerial spraying, similarly to how traditional airplanes were used back in the day, spraying from 50 or 100 meters. And for that, conclusions, I have already mentioned them all. So they are an excellent solution for some crops, not every crop, however. They do have some limitations, and that's something a lot of manufacturers mainly tend to oversee. And finally, that we have to be very careful because we still apply agrochemicals. It's a spraying application, and knowledge on what we do and what we want to achieve and the impact of what we are going to do should always be considered. And then, of course, because one might imagine that, you know, it's a new technology, okay, it works, I'm going to use it. Legislative framework should always be advised. Most EU countries have a common one. We share the guidelines, but some countries, for example, Bulgaria, decided to recently change their national framework and allow spraying drones. But again, in any case, the framework should always come first before conducting anything with spraying drones. So that would be all from me. And Fanny, I would like to ask, because I think I took some more time than I should have, is there time to show the video?
Yeah, it's a short video, right?
It's less than 2 minutes, yeah.
Yeah, you can
Perfect.
pass it. And anyway, there is no question on the question room. So I
Mm-hmm.
remember all the participants, if you have any question, you should put it on using the question button at the top of your screen.
Perfect. Thank you so much, Fanny. So here I'm going to show you a herbicide application that we conducted alongside Bayer within the project Icarus. It is a project that collaborates closely with Operate, and it has a specific national use case that has to do with spraying drones. And we collaborate with the National Crop Protection Association, and they in turn bring a lot of companies in our working group, and this actually benefits us because we have direct contact with the market. So that one specific trial, as I mentioned, has been conducted with Bayer. of course, under specific experimental permits that we have obtained from our National Aviation Agency. And we have created this nice, let's say, video that I'm going to show you. The application that we used, the herbicide that we used was Bayer's Laudis, for those that might know. And just let's just see the footage. I don't think we have sound, but let me up it. It's just music. Here you can see the water-sensitive papers, as we mentioned, that we use to assess ground coverage here. Yeah, that's all. It's actually yeah, much shorter. That's a good thing. So that would be all from me. I'm closing the screen, the sharing, and I'm back to you. Great.
Okay, thank you, Vasilis. There is no question in the chat, so
Great.
I suggest we continue with the next presentation. So now we will have a presentation from Javier Santiago, which is working at University of Santiago de Compostela, and Javier will present us the use of drone in agroecological weeding practices. Javier, you need to unmute your screen, your mic. Yeah, you're still muted, Javier. Now it's okay? No, we don't hear you. Javier, we don't hear you. Sorry for this little problem. Could you check the parameter of your mic? No.
The sound is not working for Jose. Should we carry on the next speaker?
Yeah.
Or
Yeah, maybe we can give you, Javier, a few minutes to try to find the sound, and maybe we can continue with Igor Tionov, who will present the result of the trial in Sweden, and we will come back after to the presentation of Javier.
Okay, hope you can hear me.
Yeah, right.
Great, and see the screen, right?
Yeah.
Okay, hi everyone. I'm Igor, founder of Solvi, and today I'll be talking about the different ways of mapping weeds with the drones. But first, a quick introduction for those who don't know. Solvi is a web-based software for analysis of agricultural drone imagery, and our journey started almost 10 years ago from a project with the Swedish University of Agricultural Sciences, or short SLU. And technology back then was not as easy to use. It was quite complicated, both when it comes to hardware and software. And that's how the idea for Solvi was born, to make the process of processing drone imagery and extracting valuable insight as easy as possible. So today Solvi is used around the world in over 50 different countries, and main areas are the field trials and then different plant counting applications in production fields. So how to map weeds with drones? First of all, I think it's important to differentiate the two different areas depending on what kind of weeds you want to map. The first one is when you want to map very small weeds, and especially in cereal crops that you can barely see from high altitude. So for that kind of weed mapping, usually the sampling method is the way to go, and that's how it was and is still being done traditionally, even without drones, where an agronomist would go out in the field in a few spots and do the manual assessments, and then try to estimate what kind of rate to spray the fields with. In Sweden, there was a tool developed in the 80s for that by SLU and the Swedish Board of Agriculture. That is called Dosniken, which, if you translate it literally, it's dose key. And it's a manual tool where the agronomist would make these assessments in different parts of the field and estimate the weed coverage, the crop coverage, and other factors like soil type and weather condition, and essentially calculate a score, and based on that decide the spraying rate. This tool is not widely used today, and it's not either customized for today's technology, where you have the technology to vary the spraying rate. But that's the project that, together with Thomas from AgriVest and other agronomists and researchers here in Sweden, that we initiated and conducted from 2018 to 2022, so over a 5-year period, where we tried to digitize this tool, and instead of manual assessments in a very few spots that you would traditionally do it with the drones on a larger scale. So as a part of this project, we first tested different drones and cameras and different altitudes at which the imagery could be collected, and see which gives best results. And we came to conclusion that best images are taken at 3 to 5 meters altitude, and when it comes to which density you want to collect the imagery with, 6 images per hectare, 30-40 meters between the images approximately, is what gives best results, and there is no additional benefit of taking more images. We also developed the flight planning applications to collect images in that way, because there was no off-the-shelf flight planning software to do that. And one very important aspect was also to make sure that the drones actually maintains the altitude above the ground that is required, so 3 to 5 meters, because in many fields you will have elevation differences. And if you take off-the-shelf software for flight execution, the drone will usually keep at the same altitude relative to the starting point. But if the elevation drops, you obviously need to adjust the altitude. So that was part of the application that we developed. And the altitude above ground is a very important parameter that is then used to geo-rectify the images, so create small maps so that you can do the measurements in the images. And we needed to do the measurements, like calculating number of weeds per square decimeter or even square meter. So that's why it was very important to know the altitude above the ground. So during this project, we collected a lot of images, almost roughly about 10,000 images in different periods of the year. So both in the spring and in the autumn, in different fields across the Sweden, and also in different types of crops, mainly cereal crops, wheat and barley. We annotated them manually about 500 images, where we outlined the weeds and the crops as 2 different classes, and then trained the AI model to differentiate between those 2 and detect in all other images that we collected. And then the results were, of course, reviewed by people with domain knowledge, the agronomists and researchers who know quite a bit about weed management. And then from this, so here you can see the example of one of the fields, and the green dots here show where the images were taken. So this is, I think, a 25 hectare field, and about 120 images were collected in this field. So in every image, we detected the weeds, detected the crops, calculated the percentage of the coverage, and the number of weeds, and then used also the other parameters that this dose key required, like weather conditions, type of weeds, and so on, and then created a prescription map from the same score that would be done traditionally, but compared to this approach, we had much more quality data because the images were taken much more densely that you would be able to do manually. So in this case, you can see how the rate varied throughout the field. So everything from 25% of the traditional spraying rate to 77 in the blue areas. We also done some calculations on how much you can actually save using this approach. Of course, this is not applicable in all cases, but in this specific case, a field from a place called Dumö in Sweden, we compared the outcome. So in this column, we can see how much of the product would be applied if you would do it traditionally. And then in the column to the right, how much we ended up applying with this approach. So there was quite significant difference, and in the end, it turned out to be about 25% savings in the chemicals. So instead of 900 euros, it was about 650 in money. This was also before the prices on the chemicals rise in the recent years, so probably today the savings can be even bigger. So a few key takeaways from this project. Although we had some good results in some fields, there were of course challenges in other fields and cases, and in general it proved to be quite a challenging approach. Because it's quite hard to achieve good accuracy across all this, like hundreds of images across the field, and then also in different fields in different places. There are a lot of variables that can affect the accuracy, and it's very hard to account for it. There's also no standardized approach for collection of this imagery, so we had to come up with a special flight planning app, and it turned out that in later generations of the drones that were released, not all the features were supported. So this is also one of the questionable things that can make this application hard to apply in the real world. Also, it requires quite a bit of processing, but considering that the window for application for weed spraying is quite short in these cases, so usually you want to map the field and then do the application the same way or at latest next day because the conditions can change so quickly. That makes things even harder. And honestly, like my personal opinion from seeing all other types of technology that can be applied for weed spraying, ground machinery is probably better. So cameras mounted on the sprayers that can in real time decide what is weed, what is not, and apply the chemicals differently is probably the way to go in this case. But there is another area where drones are actually a better tool. And that's spot spraying. So here we're talking about larger patches of weeds spread throughout the field that you want to locate accurately and then spray only in those places where the weeds are. For that, you would use a completely different approach compared to the sampling method. So here you would map the field, the whole field, by just using off-the-shelf flight planning software so that the drone would fly at relatively high altitude, so 40 to 50 meters approximately, but depends on the size of the patches. You would collect the images that overlap each other to 70-75%, which is again quite standard practice. And then you have a map over the whole field where it's not just some places in the field, you actually have the whole coverage and can see all the weeds in the field. And then with a tool like our Plant AI, which I will show in a second, you can, with a few examples, fine-tune some sort of agricultural AI model and detect all the weeds in the field quite easily. And then most of the drones nowadays, from the enterprise series at least, have RTK on the drones. So the maps created from these drones have centimeter level accuracy, which is really important if you want to target very small patches. But that's totally possible. So if you collect imagery with RTK drone, the maps will be very accurate, and then all the outputs that you generate from this map will be accurate as well and can be used in RTK-enabled drones or ground-based machinery. So once the map is generated, you can see here an example of what it looks like within our Plant AI tool, where you can provide just a few examples by outlining what weeds look like, and also provide examples of what crops look like, but without outlining them. Then the tool learns to detect the weeds and ignore the crops. So it's really a simple approach, and in this case, just two examples is enough to then generate the map over the whole field and detect the weeds in the whole field. So these red dots here show where the weeds were detected, and if we zoom in, we can see how the polygons outline the weeds. And this is all georeference data, so every such polygon is georeferenced with quite high accuracy. So this can work on much larger cases. So in this case, it's a field of 30 hectares that can be flown in maybe half an hour and then imagery processed and weeds detected in a few more hours. But it can also work in much larger scenarios. So this is a case from one of our customers in Australia where the fields are usually very, very large, hundreds of hectares. So I think this one is slightly above 100 hectares, but they have even larger fields quite often. And then where they want to target these patches with weeds, it has this kind of color because they use multispectral camera. The weeds turned out a bit better with it. So they use the same, exactly the same approach, and then detect all the weeds, and then have results that are ready for use for spot spraying. So in many cases, this output can be used directly, but if you want, you can also create a grid and then assign a spraying rate to the cells where there are weeds, and then assign 0 rate to the cells where there are no weeds. This approach can also be used in the field trials by, for example, chemical companies who test the different crop protection methods. So manually assessing the weed coverage this is quite small field trials, just a few plots. But if you have a few hundred or even 1,000 plots, it can be quite time-consuming task. So now it's quite becoming more and more common that they use drones instead. So they just map the whole trial area, use the same tool to identify the weeds, like we see here in the image to the left, and then calculate the percentage coverage for each individual plot. So they can do it much quicker and with greater accuracy. A few takeaways about this approach. So this is a method that actually already used out there in the real world. And why it works is mainly because there is nothing special that is required to be developed. So drone pilots or agronomists or whoever uses the service can just use any flight planning applications to map the field and choose the altitude that is required so that the weeds are visible. And it works also with most drones and cameras. So you can use Mavic 3 multispectral, or you can use a fixed wing drone to cover larger areas. So you don't need any special hardware for that. There's also usually is not as urgent to do this spraying. So if you need to process a lot of data, it's not a problem if it takes 2 or 3 days. So that simplifies things a bit as well. And in this case, the drones are really right tool for the job. So you can map quite easily whole fields, but then also, as we've seen in previous presentations, spraying with the drones is also becoming quite common nowadays, and that's where really can make quite big changes, not just in chemical inputs, but even when it comes to using the what is it called, the safe on the fuel. So with that, that's everything I had for now. If anyone is interested in trying the drones and start analyzing the imagery in their trials or production fields, we have a few articles on our blog where you can dive deeper into more specific topics. And if you have imagery and want to try it out on your own, you can always sign up for a free trial on our website, which is solvi.ag. Thank you. And if you have any questions, I'll be happy to answer.
Yeah, thank you, Igor. In fact, yes, there is one question. Based on what data you make a decision to reduce the dosage? With density? Or do you, I think it's relating to
To the first approach, yeah.
the first, yeah. Or do you change the percentage of spraying by reducing the pressure or changing nozzles?
Sorry, can you repeat the last part?
Or do you change the percentage by reducing the pressure or by changing nozzles?
That's a good question. I'm unfortunately a bit far from the practical application, so we were more focused on the imagery analysis part. I don't know, maybe Thomas knows the answer to these questions. Thomas was also part of this project. But when it comes to yeah.
Yes, I don't think I can go so deeply into it either, but it was the the water, the amount of water that you reduced if you had a lower dosage. So you had yeah, it was actually the pressure, and that influenced how much water you applied on that spot in the field. So in that sense, it's correct that you you change the pressure in the sprayer.
Yeah. Okay.
If that is enough for now.
And to calculate the dose, so one of the parameters in this tool was to calculate number of weeds under, like traditional, under the palm of the head, which is very tricky also from the drone imagery, because very often the weeds are not fully visible and they overlap. So if you go out in the field and do it manually, you can do it probably better. But with drone imagery, it can be sometimes challenging. But that's what we use. So we calculated number of weeds per square decimeter and then extrapolated it over larger areas. But then there were also other parameters as well.
Yeah, it was very simple solution really. So you didn't change nozzles or anything like that. So the technique were all the same.
Okay. And I have another question. Which is the best stage of the weeds to do this detection? When it's plantlets, I guess it's more easy to detect and to distinguish between the weed and the crops. And what about when it's more like young plants? Is it more difficult for the drone to make the distinction between the crops and the weeds?
Yeah, we have tried it in quite different stages, really, but quite young plants from DC 22 to 31 or something like that. So,
Okay.
when you normally make the sprayings, and most of the time it was in spring cereals that we have been working.
Yeah, typically it's as long as you can see the weeds. So you want to catch the growth stage when you still see the weeds from above. And that's also the tricky part, because if it rains and then if it's warm, like a lot can happen in just a single day. So you really need to time the flight correctly to be able to use this application.
Okay. There is no more question on the question room, so we can continue. We will try again with Javier presentation. Javier, did you manage to find your sound again? Or no? Yeah, Javier. Yes.
Sorry, do you hear me now?
Yeah, perfect.
Okay, sorry about the previous problem. Then I'm going to speak about the drones as a cheaper uh, way to found the weeds. Uh, there is a strategic European plans to reduce the herbicides, the use of the herbicides. Um, we need to know where is exactly the weed to use less herbicide. We, the objective is monitor it with drone or satellite um, image to know where is the weed. So the satellite images are cheaper, but they have problems as interference of clouds, and the resolution problem is essential to know where is the weed. And then we can use drones by, from the system we can use is from the bands of the drones, of the photograph, the visible spectrum and the infrared, but we can use different index. In this image, we can see a plantation in the northwest. We can see yellow flowers and red flowers. In the southwest, we can see only red flowers. It's because the northwest is free to grafted plot, and the southwest is a grafted plot. Then there is a difference. The animals take the plants with yellow flowers are legumes and don't eat so the red flowers as Erica. We can use index and you can see as NDVA. NDVA is index used near infrared band and red band, and and it's very useful to know to take to the chlorophyll. The same is with the GNDVA with the green band. There is a lot of index. You can take the link in this web to know it. But we think a cheaper solution to know what is the width with RDA or visual image. And this is a composition in RDA, three mass to overpose, putting the three bands. But we can use the visible bands to know where they are. For example, green leaf index is very useful to know the chlorophyll is the plant health, but not. We can see the flowers as a green, a dark points here, and the shape index is very useful because it's based on red band, and we can see here the plots with the red flowers, and now so clear the yellow or dark and green. Index based in the red band, we can use directly red less blue band to know the red flowers and the yellow. RLSG, RLSG is identified similar also red and yellow flowers. The green less blue can identify the yellow flowers better than the red. So the index as TGI, sorry, can identify better the yellow flowers. If we use the visible index, we can see over over a globe between the range of legumes or yellow flowers and erica in G less B and E in R less B, but there is no over position over slab on red and green or in TGI. Then we can differentiate the legumes and ericas with this index. As we look for the correlations between the index, we can see there is a lot of correlations, but in ericas, the TGA and the if are few correlations with the other index. And then satellites is a required monitor to large vegetation types, but the drones are associated with index is required to monitor with a plot scale. And then, and this is all. Thank you.
Okay, thank you, Javier. I'm very sorry, but we had a lot of questions. In fact, we had some technical problems, so the question didn't appear, but we have all now. So I try to take it from the beginning. So we have a question for Vasilis, I guess. It's a question about do we need a specific preparation of herbicide solution to spray with drone? Are you still here, Vasilis? Or maybe Thomas, or I don't know, Igor, if you already made some spraying with drone, maybe you can answer the question. There is also a question on if spraying with drone is allowed in Sweden.
I can answer that because that's what I do. But
Yeah.
definitely it's not allowed, but we are working on it, and you will hear a bit more about that in my presentation. But for now, it's not allowed, but we may be able to start some testing by next year. But it's going to definitely be a testing phase before it opens up for everybody.
Okay. And what about the herbicide formulation? Do we need a specific herbicide formulation to spray with drone? And is a new herbicide formulation could be mitigated drifting issues? It's for you, Vasilis, I guess.
So, first of all, apologies, I was outside. Can you please repeat the question? Because
The question is, do we need a specific herbicide preparation to use in the drone, and if there is a new herbicide formulation, can mitigate drifting issue?
So, drifting issues, I will start with the second one. Drifting issues are not that related with the herbicide consistency, let's say, or density itself. It is more of an equipment preparation or selection, even. So, for example, the nozzle type and the operational parameters that we decide to apply this agrochemical with. So, it's not directly related to the chemical itself, but how we use it. Now, for the other question, that if there is a specific label for drone usage, the answer is no, because in EU grounds we are still waiting for the legislative barrier to be lifted, and the companies, the agricultural manufacturers, to be able to produce these labels. And this is why a lot of companies are actively involved in our research, because they also want this to happen. They want to be able to produce these new chemicals that are specifically designed for drone usage. And for the first question, for the preparation of the agrochemical itself, there is one specificity. So, for example, the mixture process, because most drones, for example, I'm talking about DJI, the Chinese manufacturer, which is by far the largest one in the world, they do not come with a mixturing system integrated. So, to this end, it's usually a good practice to prepare the mixture in a different larger tank, and then this tank slowly refill the smaller tank of the drone little by little. And occasionally, for example, if you have a very large application and you prepare enough mixture for, I don't know, 30 or 40 hectares, it might be a good idea in the middle of the operation to repeat the mixturing process to ensure that there are no solid parts, let's say, formatted in the lower parts of the tank. So the mixturing is the only thing that should be prepared carefully, because as conventional sprayers that have the system integrated, drones do not have, and you have to prepare them in advance and then just proceed with filling the finalized mixture directly to the drone.
Okay. And another question for you, Vasilis, related to drift. Why terrestrial spraying causing drift is much higher than drones? And what is the type of sprayer used?
So normally the most trials are conducted with a standard application in Greece. The experimental trial, the crop I'm going to talk is mainly vineyards, because this is where most of my research has taken place. And when we go to comparing a new technology with a standard one, we usually use the standard one. So the one that is normally used by the average producer in that area. In that case, the vine sprayer that is used, the boom sprayer, the mist sprayer that is used in the experimental field that we conduct the trials is a standard, almost 15 years old. It's quite an old piece of equipment, mist sprayer that operates at 10 bar, which is quite high, and it has a total volume of roughly 600 kilograms, so 600 liters. What was the question again, Fanny? Because I started, sorry for that, I started answering.
It was why the drift was different between terrestrial drift and drone drift. Why the
Yeah,
terrestrial one was higher?
yeah. So for me, there are two reasons to explain this. The one is that, as mentioned in the presentation, the UAV is in a much better position to mitigate drift because of the downwash. So if you check most agricultural drones, the nozzles are positioned directly below the copters, the rotor blades. So they are positioned like that because they want the downwash to affect the droplets. They want to also push them inside the canopy, and they want to create this barrier, as we said, that prevents them from escaping and going left and right, which creates drift. But a very different, let's say, critical point is that the orientation in the mist sprayer of the nozzles, it creates something like a circular angle. So droplets especially when we talk about the turbine sprayer, when the turbine is active, it's exceptionally positioned to push them away, in an essence. So it creates drift in a much higher distance. And also, we talked about the dilution rates. So because in drones we have a smaller tank, this actually means that we have to make a thicker, a more dense mixture. So instead of spraying 20 or 30 liters per hectare, per strema, so 400 per hectare, we end up with a much lower dosage of 50, for example, liters per hectare. So just by having such a difference in application rates, this creates smaller drift. If there is a similar phenomenon, for example, in conventional ones where we create the thicker mixture and the larger droplets, um, for example, with anti-drift nozzles, if you use anti-drift nozzles and conventional ones in a mist sprayers, the conventional ones will have much higher drift as we move further from the application area, although the anti-drift ones will have higher drift close to the area because the thicker droplets, the larger ones, end up falling close to the last line of application, and that increases it. But in drones, we talk about a different system entirely. The positioning of the nozzles is different. The application rate is much smaller, and that combined produces a much better and much more desirable drift profile. So, yeah.
The last one regarding to drift, did you try to
Mhm.
use an adjuvant to reduce the drift?
Not yet, not yet, because there are so many things to try that we first try to eliminate every operational, let's say, aspect because before we move to the characteristics of the mixture itself. And because, as I mentioned right now, we don't even use agrochemicals in most cases because we want the experiment to be as safe for the researchers as possible, and it's because it's the normalized procedure. We use either tracers, color tracers, tartrazine, or deionized water. So once we move towards, let's say, a complete database of sensitivity tests of how parameters affect the final result of the spraying, we will then move towards the liquid itself, towards the liquid engineering aspects, which in my opinion will play a role. And this is also something that the companies are interested in because there is this notion that in drones I can make a very, let's say, dense mixture, but in the end of the day, there is the small risk of blocking the nozzles. So if you create something very thick, you end up, it's borderline not liquid. It's very rare because in most cases you still use small rates of agrochemicals, not enough to create such a thick mixture to block the nozzles, but it's a risk that is present. So yeah, to answer your question, we haven't started yet. We plan to.
Okay. Thank you, Vasilis.
Thank
We
you.
have some question for Igor. For plant IA, the farmer would annotate only few images and train a new model specific to his field. And does this method also work for weeds in green meadows, as detecting sparse weeds between crops is easier than identifying weeds surrounded by green meadow?
Right. Yeah, I already received this question by email.
Okay. Perfect.
But I can answer yes. So you fine tune this base model that we have behind the scenes that is already trained on a lot of agricultural data. And it happens in real time. So maybe it takes 15, 20 minutes to make an iteration where you provide a few examples, you run detections, you see what it looks like, and then you can refine the results. But that's usually the process, yes. And then it works on in all scenarios where you can somewhat clearly see the weeds. So even in green on green scenarios, as long as you can see some sort of unique pattern about the weeds that you want to identify, you can train the AI to detect it.
Okay. And there was also a question regarding, could you explain why the time window was shorter in the first method regarding the one of spot spraying methods? We have to do the map and the spraying on the same day, right? On the first method.
Yeah, I mean that's usually how it is. Yeah, so when you spray cereal crops, you want to spray it at certain stage, and like I said, a lot can happen in just like 1 day or 2 days, depending on the weather. If it's warm, the crops develop very fast. So that's why timing is really important. In for spot spraying, like there are so many different ways of doing it, and you can do it after the season, after the crops are harvested, and you can clearly see, for example, patches with thistles, and there is usually no urgency. You can do it today, you can do it in a few days from now. Like it's not that as urgent as it is in spring applications.
Okay.
I hope
And
we
the
have some
last,
time for Martin's presentation as well.
yeah, we last one, and after we will take Martin. What are the parasitic weeds that cannot be seen until damage occurred? For example, broom rape. For you, Igor, I guess.
Is that a question for me? No,
Yeah, yeah.
I'm not an expert in this.
Okay. But we can continue with Martin presentation. Emma, the webinar will be automatically closed at noon, or can we have some time?
No, we can still have some time.
Okay.
Okay, do you hear me?
Yeah.
Yeah. Okay, my presentation is not that long, so there will be some time at the end as well. Welcome to this presentation. My name is Martin Braun, and I'm the founder of Spray Drone. And I've been spraying Sweden green with water since 2020. So we were 4 years too early to the party, and unfortunately, the party hasn't started yet. Let's see. You have the good here? The good, let me see.
Can you put you
No.
in
Okay,
presentation
here.
mode? Yeah.
All right, okay. So Spray Drone started as a heavy lifting drone builder, and in 2020 we built the Viking 8. It was a beast, and it could lift 70 kilos, which was a lot in 2020. This drone got a lot of publicity, and we got contacted by many agricultural and forestry companies. And we even built this spray boom on it, and we were ready to go. Unfortunately, after doing more research, we realized that this was not going to be so easy. And the offenders are right here. And I have no problem understanding why the regulation came in when you're looking at this photo. But the reality is a little bit different for us today. We have done many demonstrations over the years, and 2 months ago we did a demonstration with all the government bodies that makes decisions in Sweden, and they were very positive to testing and starting, but we still have a little bit ways to go. But I have some other positive news actually from Finland. Finland just came out from the government and said that we're going to start full on with testing with drones and spraying from next year. So I think it's just a matter of time before everybody starts with this, and I think we're really close. But at least some countries have to start, and the other ones would follow. And it's very good news that Finland is now starting. So while we're waiting for the approvals to get started, the drones and the system keeps on getting better and better, and especially the precision. We've been using the DJI products for the last 3-4 years, but it was only when we started using this new drone, which is called the Wonder Drone, that we see the real potential of the spraying drones. It is open source, so it's much more easier to set up particular projects. If it's something that is a little bit different than the typical DJI spot spraying or normal spraying, then it's very, very complicated with DJI because it has a locked system But with the open source, we can do many interesting projects, and I'm going to talk a little bit more about that later. So I'll put the video on here. Of course, the drone is fully automated. And what is kind of cool with this drone is that it has a spot spraying application. And the secret sauce to this drone is that more than 95% of the droplets are identical. Which you see here, the spraying picture is perfect. And you can set the droplet size and the amount on the controller. So you never have to change your spraying systems. It simply automatically changes the droplet size on the controller. And they built this drone just below 25 kilos, which makes it a lot easier for certification and a lot easier for the farmer to operate. And this is why this is kind of nice, because the sprayers are getting a lot better. If you can compare this patented sprayer that we have on the Wonder Drone compared to the DJI T30, you cannot even compare at all. This is just absolutely, you can fine tune your droplets. And also another nice feature of this drone is that you can fly much lower than the DJI drones, which can eliminate more wind drift. And you can go all the way down to 1 meter with this drone. So how do we detect the weeds? We use a similar company like Solvi to do that. The company's name is Proofminder. It's also a Hungarian-based company. And we are at the moment building a library of weed algorithms with them. And we also use the same picture recognition to create these AI algorithms. But the nice thing, which also Igor said that he can do, is that when the algorithms is set, all we need to do is scan with the drone, and we get the result of where the weeds are. And it also comes into like a work file. So all we need is to download this shape file into our spraying drone and decide how much liquid we want to put out, and the droplet size. You put and you decide how high you want to fly, how fast. You put go on the controller, and it would automatically go and spray all the patches of weeds. So this is the other project. It's not exactly weed, but I just wanted to real quickly go through it, so you see that this kind of concept with the AI and spray drones and how they talk to each other together can open up a lot of new projects. We have a lot of problems with the moose eating up the forest in Sweden. And for that reason, we keep the amount of mooses at a very low level, because it's hundreds and hundreds of millions of euro each year revenue lost for the Swedish forest owners. And the moose, his favorite is the new planted tree. So what he does, he goes and he bites on top of the new planted tree. And what happens?